Yeah, welcome. So in this lecture, we'll be discussing some practical problems on paging. Okay, so let us see some examples. See this question. Calculate the size of memory if its address consists of 22 bits and the memory is 2-byte addressable. So what does it mean? First, let us try to understand the question. So calculate the size of the memory if its address consists of 22 bits. That is, to address a particular memory, to to address a memory, we are using 22 bits. Okay, to address a memory we are using 22 bits, right? And and another thing is, it is 2-byte addressable. 2-byte addressable means what? 2-byte addressable means each byte, each location is 2 bytes. Okay, the size of each location is 2 bytes. Okay, that is 16 bits. Each location is 2 bytes, right? So that is the meaning of 2-byte addressable. And the address 22 bits means each location is represented using 22 bits. So for example, the first location will be represented using 22 zeros, 0 0 0 0 0 up to how many zeros? 22 zeros. The second location will be also 22 bit 0 0, the last one will be 1. So there are totally 22 bits used. Okay, and the memory is 2-byte addressable. That is, each location is 2 bytes. Okay, but the question is calculate the size of the memory. Calculate the size of the memory. Totally, how many locations are there? Okay, how many bytes are there? Not locations. Totally, how many bytes are there? Okay, how many bytes of memory is available? That is what you have to calculate. Okay, so first we should know how many locations. We should know how many locations. Then we can multiply with 2 bytes because each location contains 2 bytes. So how will you calculate how many locations? So the number of locations is connected with the number of bits that is used to represent each location. So here it is given in the question that each location is represented using 22 bits. That is, the memory is addressed using 22 bits. So using this, we can calculate how many locations. Using this, we can calculate how many locations. So how many locations means it is just 2 to the power 22 locations. It is just 2 to the power 22 location. Okay, and each location is 2 bytes. Each location is 2 bytes. Okay, so so you multiply 2 to the power 22 by 2 bytes. Okay, multiply 2 to the power 22 by 2 bytes. Okay, so 2 bytes is nothing but okay, multiply 2 to the power 22 by 2 bytes. So that is what we are supposed to do. Okay, so say for example, so what should we do? We should multiply 2 to the power 22 by with 2 bytes. Okay, so let me calculate 2 to the power 22. So here I am calculating 2 to the power 22. Okay, so it is coming this value 4194304. Okay, multiply this. So this many locations are there, but each location occupies 2 bytes, so multiply it with 2. Okay, so totally your memory has this many bytes. Okay, let us try to convert this into megabytes. So so th- so this is the size of the memory. So we already find the answer. This is the answer, but it is in terms of bytes. So totally, with 2 to the power 22, with 22 bits to refer to the memory, and if each location occupies 2 bytes, then totally how many bytes will be there? In the sense, this many bytes will be there. Okay, how many kilobytes will be there? Just divide this by 1024. That many kilobytes will be there. Okay, so there will be 8192 kilobytes. How many megabytes? This is equivalent to how many megabytes? Again, divided by 1024. So that many megabytes. So that is equal to 8 megabytes. Okay, So in this case, the answer is 8 megabytes. Using this 2 to the power, using this 22 bits, and if each location is 2 byte, you can address how many locations in the sense. Totally, the memory size is 8 megabytes. Now consider this particular problem. Calculate the number of bits required to address 16 GB memory. Okay, calculate the number of bits required to address 16 GB memory. Assume the memory is 4 byte addressable. Okay, calculate the number of bits required to address 16 GB memory. Okay, here the memory capacity is given. Here the memory capacity is given. We are asked to identify like how many bits are required to address this particular memory. Okay, the size of the memory is 16 GB, and each location occupies 4 bytes. Okay, so it means you have a memory location. The starting location is 0 and the ending location is 16 GB. Okay, so this memory capacity is 16 GB. Okay, and each location, the size of each location is 4 byte. If you take one location, it is 4 byte. 4 byte means how many bits? 8 8 fours are 32. 32 bits. Okay, 32 bits forms uh, one location. Okay, that is 4 byte. Okay, now the question is number of bits required to address this memory. So we need this many addresses, 1 2 up to 64 GB. Are you getting? So first you have to identify how many bits you require to address 16 GB. Okay, that you have to divide by 4. Okay, because each location contains 4 bytes. So we need not require that many address bits. We need that identify how many bits are required to address 16 bits, that you 16 GB memory, that you divide it by 4. So that will be the value. Okay, so here in this case, what should we do in the sense? First, we have to convert 16 GB to, first we have to convert 16 GB to what you call, we have to convert 16 GB to byte. Okay, let us convert 16 GB to byte. So 16 GB means how much MB? Multiply by 1024, that many MB. Okay, how much KB? Multiply this by 1024, that many KBs. Okay, how much bytes? Multiply again this by 1024, that many bytes. Okay, right? So 16 GB contains this many bytes, this many locations. So this many locations. Okay, so but we know that each location is 4 byte. In the question it is given that each, assuming the memory is 4 byte addressable, it means each location occupies 4 bytes. So divide this by 4. When you divide this by 4, what you get is this many locations. So totally the memory contains this many locations, where each location is of 4 bytes. So how many, now we have to identify how many bits are required to address this many locations. Okay, so how many bits are required to address these locations? So that we have to identify. So we can do some error and trial. Say I am trying 2 power 20. 2 power 20 is, it is not sufficient. Okay, so say let me try 2 power 30. It is coming somewhat close. It is coming somewhat close. So I can try 2 power 32. So if I try 2 power 32, it is 429496729, exactly this. Okay, so it means how many bits are required? 32 bits are required. 32 bits are required to address 16 GB of memory if the memory is 4 byte addressable. That is, each location occupies 4 bytes. Okay, so the answer is 32 bits. Okay, fine, right. Let us consider this another problem. Consider a system with 4 byte addressable memory. Okay, that is, each location occupies 4 byte. Each location occupies 4 byte and 32 bit logical address. The logical address is the logical address contains 32 bits. Okay, and 4 kilobyte page size. The page size is 4 kilobyte, and each entry in the page table. Okay, this is page size, this is page table. Okay, each entry in the page table occupies 4 bytes. Okay, now what is the size of the page table? Okay. So first, again, let us be very clear with the question. So here the question, what it says in the sense, consider a system with 4-byte addressable memory. So what does it mean? It means that there is a system with some memory, okay, with some memory, where each location in the memory is 4 byte. Okay, so this is 4 byte. So that is the meaning of the first sentence. Sorry, consider a system with byte addressable memory. I'm sorry, consider a system with byte addressable memory. That is, each location is 1 byte. Okay, so this is memory where the memory is divided into several locations. Okay, and each location is 1 byte. That's all. Byte address means just 1 byte. So each location is 1 byte. Okay, and 32 bits are used for logical addressing. Okay, 32 bits are used for logical addressing means, what is the logical address space? The logical address space is then 0 to 2 to the power 32. Okay, the first location will be 0 and the last location will be 2 to the power 32. So that many locations will be there. That many locations the logical address space can address. Okay, 4 kilobyte page size. Okay, 4 kilobyte page size. What does it mean? What does it mean in the sense, we know that the logical memory will be divided into several pages. See, this is actual main memory. Okay, this is actual main memory. In main memory, the memory is addressable in as bytes. Okay, the main memory is addressable as bytes. Okay, so let us not confuse that thing with this. And this is the logical address space. Okay, the logical address space is divided into several pages. Okay, where each page is of equal size, right? And the first location is 0th location, and it can maximum address up to 2 to the power 32 locations. Okay, so this is the logical address space, right? And in the logical address space we have page. Okay, and what is the size of each page? 4 kilobyte. So if you take one page, its size is 4 kilobyte. The size of one page is 4 kilobyte. Okay, and page table entries of 4 bytes each. So we have page table. So this is actual main memory, this is logical memory, this is page table. Page table is what? Page table is the one which maps the logical which maps the page number to the frame number. Okay, page table is something which maps the page number to the frame number. Okay, to the appropriate frame it maps. In the main memory we'll have frames. Okay, so so in the page table, so page table will also have many entries. Okay, so for page 0, what is the frame number? For page 1, what is the frame number? For like that it will have. But each location in the page table, each location, that is each entry in the page table is 4 byte. 4 bytes. Okay, 4 bytes. Right? So this is the given thing. Now the question is the size of the page table. We want to identify the size of the page table. What is the total size of the page table we want to identify? For that, what should we need? We know individually each location, how much a location it is required in the page table. Individual entry in the page table needs 4 bytes. So how do we calculate the total size of the page table? For that, we should know totally there are how many locations. It may be up to 0 to n minus 1. So in that case, what is that n that we should know? If we know that n, then you just multiply that n with 4 bytes. That is the answer. Okay, but we don't know this n. This n is the one we have to calculate. So if you identified n, multiply this with 4. Okay. So how do we do that? So consider a system with a byte address memory, 32-bit logical address. So it means if you remember the theory, whatever we have discussed, it means m is equal to 32. The logical address space, the number of bits used in the logical address space uh, is represented as m. Okay, so m is nothing but 32. Okay, and the size of the page size is 4 kilobyte. So 4 kilobyte is not 4 kilobyte is what? The size of the each page is 4 kilobyte. 4 kilobyte is nothing but 4096 bytes. Okay, 4 kilobyte is nothing but 4096 byte, which is nothing but 2 to the power 12. 4096 is nothing but 2 to the power 12. Okay, so this is nothing but n. So if you connect with our theory where we initially discussed the concept of page table, so this is n. So m represents the, what you call, the number of bits used to address the logical memory, and n represents the number of bits used to address the the a particular page. Okay, so each page can be addressed using 12 bits. So n is equal to 12. N is equal to 12. Okay, now the logical address space, now the logical address, it will have how many bits? Again, if you recollect, the logical address, it will have two parts. M minus n bits, m minus n bits will be used to refer to the particular page number, and the remaining n bits will be used to refer the offset. Okay, so m minus n is what? 32 minus 12 is 20 bits. So this first 20 bits, the higher order 20 bits will refer to the page number, and the lower order 12 bits will refer to the offset. Okay, lower order 12 bits will refer to the offset. So 20 bits we have to refer to the page numbers. So to refer to various page numbers, how many bits we have? 20 bits. So using 20 bits, how many locations we can address? That is the question. Using 20 bits, how many locations we can address? We can address 2 to the power 20 locations. So basically, using 20 bits, you can translate 2 to the power 20 pages to the respective frame numbers. So here, so the value of n is nothing but 2 to the power 20. Okay, value of n is nothing but 2 to the power 20. So what is 2 to the power 20? That we have to calculate. So you can calculate what is 2 to the power 20. Okay, so let me erase the unnecessary things. Yeah, so we have to calculate what is 2 to the power 20, right? Yes, so just calculate 2 to the power 20. So 2 to the power 20 is how much? 2 to the power 20 is this much. Okay, 10,000, so whatever it may be. Okay, so 10,48,576. Okay, so this many locations can be in the page table. Okay, the page table can have this many locations, where each location occupies 4 bytes. Each location occupies 4 bytes. So multiply this by 4. Multiply this by 4. Okay, so totally the size, this is the size of the page table in terms of bytes. The page table can have this many bytes, 41,94,304 bytes. Okay, but we need the answer in megabytes, so we should convert this to megabytes. Okay, so how can we convert this to megabytes? So this is bytes. So to convert it to kilobyte, divided by 1024. To convert this to kilobyte, divide this by 1024. So this many kilobytes. Okay, again divided by 1024. So that many megabytes. Okay, so which is equal to 4. So the answer is 4 megabytes. So the size of the page table will be 4 megabytes. Okay, right? Yeah, come down. Not here, this. Yes, so this is the answer, 4 megabytes. That is option B. So here option B is what? 4 megabytes. So that is the correct answer. Okay. Let us discuss one more example, which is a little tricky. Okay, consider this. In a virtual memory system, virtual memory is nothing but the logical address space. Okay, size of the virtual address is 32-bit. Okay, size of the virtual address is 32-bit. That is logical address, which is 32-bit. Okay, the size of the physical address is 30-bit. That means what? In the sense you are using 32 bits to refer to the logical address. That means you are using 32 bits to refer to the logical address. It means your logical address space is more than the physical address space. So logical address space, it starts from 0 to 2 to the power 32 locations. That is the meaning. Okay. So this is, let me call this as logical address space. Okay. But the physical address space, let me draw here. But the physical address space is only 30 bits. So it means the physical address space, it starts from 0 to 2 to the power 30 bits only. So it means the physical address space is not that much. The logical address space is higher than the physical address space. Okay. The page size is 4 kilobyte. Okay. Page size is 4 kilobyte. Page, normally we use the term page in logical address space. Okay. But page size, frame size, both are same, right? So page size, in the sense you can take it as frame size also. So it is 4 kilobyte. So each page size, so there are many pages. Okay, there are many pages. The logical address space will have many page. Each page is of 4 bytes, 4 kilobytes. Sorry, each page is of 4 kilobyte. Okay, and page size is 4 kilobyte, and the size of each page table entry is 32-bit. Okay, again page table. The page table, which translates the page number to frame number. Page table is the one which translates the page number to frame number. Okay, so each page table entry, every entry in the page table is 32 bits. Every entry in the page table is 32 bit. Okay, so this is the context. This is the context. Okay, the main memory is byte addressable. Okay, that is, in the main memory, each location represents 1 byte. Each location represents 1 byte. Which one of the following is the maximum number of bits that can be used for storing protection and other information in each page table entry? Okay, so don't get confused with the question. Actually, we should identify how many bits in the page table. You see there are 32 bits, but we should identify how many bits are required to address this physical memory. That is what we have to identify. Okay, so let us calculate the m and n. What is m and n here? We see with respect to logical address. First, let us calculate with respect to logical address. With respect to logical address, m is 32. M is 32. N is, each page size is 4 kilobyte. 4 kilobyte is nothing but 4096 bytes, which is nothing but 2 to the power 12. So n is nothing but 12 bits. N is nothing but 12. Okay. So I think you are getting, because 4 kilobyte is nothing but 4096. 4 kilobyte is nothing but 4096. Okay. 4096 is nothing but 2 to the power 12. Okay. So 12 bits are required to address a particular page. Okay, so n is 12. Okay, so to address this particular logical memory, how many bits is required? We need m minus n bits here. Okay, that is 32 minus 12 is 20 bits to refer to the page number, and 12 bits to refer to the offset. 12 bits to refer to the offset. Okay, this is the scenario for logical address. But finally we want to access which address? Physical address. Coming to physical address, what is the value of m? Coming to physical address, the m value is 30. Okay, what's the value of n? N is same 12. Okay, so to address the physical memory, what should be the size of the address? So in this case m minus n is what? 30 minus 12 is 18. Okay, so physical address of the entire physical address space, all locations can be accessed with 18 bits, and for offset we need 12 bits. Okay, that is, each locations of the physical memory can be accessed using 18 bits, right? And for offset we need 12 bits. Okay, so now see, this is the crux. Each location of the main memory, each location of the main memory can be accessed using 18 bits, uh, because there are how many, because each location means what? Each each the memory will be divided into several frames. The memory will be divided into several frames, where each frames occupies 4 kilobytes. Where each frame occupies 4 kilobytes. So one location represents 4 kilobyte. Another location represents another 4 kilobytes. Okay. So totally all these locations can be accessed by using 18 bits. But here, if you see in the page table, each entry is 32 bits. This 32 bits is not required. We need only. So what is 32 minus 18? So 32 minus 18 is what? 14 bits. So we have 14 extra bits. Actually, we need only 18 bits to access the particular physical memory, but we have 14 extra bits. So this 14 extra bits can be used for anything else. So that is the question. How many, what is the maximum number of bits that can be used for storing, protection and other information? So for protection and other information, you can use this extra bits, which is 14 bits. So the answer is 14. Okay. So, so this is about this particular question, right? So here, if you want, you can check the answer. The answer is 14 bits, right? Fine. Let us stop here. Thank you.